So L5.2, parameter interpretation. Now, before we go on to interpret parameters, I want to give or introduce a motivating example that we're going to use throughout the lecture. This is the application we're going to look at in part 5 of the lecture, and it's to do with analysing journey times on the London Underground. So let's say I'm interested in how long trips take by London Underground. I'm visiting friends, or I want to visit friends across London, and I want to know how long it's going to take to travel by tube between various destinations. And I'm thinking about what it is that might influence my journey times, and I come up with some hypothesis, and that is that the frequency of service is going to matter. So how long am I going to have to wait on the platform for a train to arrive? That's going to influence my journey time. Secondly, I think congestion is going to make a difference, because that will depend on how quickly I'm able to traverse through the possibly crowded system. If the system's very crowded, it's going to take much longer than if it's less busy. Another influence is going to be how familiar am I with the OD route? Have I travelled that route before? And if so, do I know the quickest ways to get through the route? And finally, it's obviously going to depend on what distance I want to travel. So how far across London do I need to travel? Now, in order to get a good understanding or be able to predict my journey times, which is what I want to do, I need to account simultaneously for all of these variables. Each of these variables is going to affect journey time simultaneously, or if you like, in combination. And this is the principle underpinning multiple linear regression. I have multiple independent variables that affect my response. In this case, frequency of service, congestion, familiarity, distance. And I have a single response that I'm interested in this case, journey times. So let's say that, well, in fact, I do have data on London Underground. I have historic data on London Underground trips that would allow me to build a regression model to predict or make inference about journey times. And this regression model is just going to try and represent these hypotheses I have about the things I think will influence my journey times. So the London Underground data we're going to use in this lecture contain information on passenger trips across 444 origin destination pairs. So trips from an origin station to a destination station from 6 AM to 12 AM over a 7-week period. There are n trips indexed by I, and for each trip the data records the journey time, so that's the travel time between the origin and destination pair in minutes. That's going to be our dependent variable, that's going to be y. It records headway. A headway for trains or subways is the temporal duration between trains arriving at stations in minutes. In other words, this is essentially train frequency. It records line loading, or what we're going to call load. This is the abbreviations that we're going to use. That's the average number of passengers on the OD pair during the passenger trip, and we normalise that by the daily average numbers on the OD pair. So this variable here is giving us the measure of congestion, or how crowded the system is, that OD pair is. We've got our record of passenger history, so for each trip we know the number of repeat trips that the passenger has made on the OD pair. So this tells us the familiarity that the person making the trip had with the OD pair. And finally, we have the distance in kilometres between the origin and destination station. So using these data, we could form a multiple linear regression as follows. The dependent variable is journey time, indexed by I, so journey time for trip I. Beta naught is an intercept, and then we have 4 independent variables that correspond to our hypothesis. Headway, which corresponds to frequency, the idea that frequency will affect journey time. Load, which corresponds to congestion. Passenger history, which corresponds to familiarity. And distance, which just simply says that for longer distances we expect journey times to be longer on average. And finally we have an error. Now in lecture 4 we introduced the multiple linear regression model already, actually, using this notation. So with k independent variables, x1 to xk, excuse me, we wrote the multiple linear regression model as conditional expectation of y given x1 to xk. Y is the dependent variable, xj is the jth independent variable, j equals 1 to k, and beta j is the jth unknown parameters. So there are k plus 1 parameters, a parameter for the intercept, and then j parameters corresponding to each of the independent variables in the model. Now, generally speaking, there are two reasons why we might want to estimate a multiple linear regression model. And in one of the textbooks for the course, called Introduction to Statistical Learning, this distinction is made quite well, so I encourage you to look at that. The first reason we might want to estimate a multiple linear regression model is for prediction. So in some situations we observe the covariates x1 to xk, but not the outcome y. So using observations for which we do know y and each x, we could estimate our multiple linear regression model and then use the resulting estimates to predict our missing y's. Now, in what sort of situations might we know x but not y? Well, it might be a situation where we know how x is going to change in the future and we want to predict what that's going to do to y. So we build a model, let's say this model here, using today's data for when we can observe both y and all the x's, and then we predict y for the future by plugging in a new x that we expect to happen. Another example could be that we've got data on y and all of the x's for some particular empirical context. It could be some city, it could be some region, it could be some country, and we want to use the model that we develop using data where y and x is observed to predict the missing y's in some country where we don't observe them, or some city, or some household, whatever it might be, whatever the different context is. Now, in settings when we're just interested in prediction, we care mainly about y hat. We don't really care too much about the individual values of the betas themselves. They're less relevant. What we really care about is the prediction. So for example, in our case where we're looking at journey times, let's say that we don't observe the journey time from Old Street to Holborn. We could use a model that has been estimated for places covariates to predict how long it will take to travel from Old Street to Holborn, as long as we observe the x vector for that trip between Old Street and Holborn. We can predict the y on the basis of the estimated parameters of the multiple linear regression model. Okay, that's the first purpose that we might want to put regression to, and that's prediction. The second is inference, and inference is all about, rather than predicting, about understanding the association between y and each individual component of our matrix X, each individual xj. So we want to know how y is related to each and every xj in the model. And so the sorts of things we're interested in are which covariates are actually associated with the response, which are not associated. In what way are they associated? Is it positive or is it negative? What is the magnitude of the relationship? And that's what the beta j's are going to measure. So in this setting, we do care about each individual parameter estimate, beta j, hat beta j, and we're going to use them to draw inference about the effect of each xj on y. So in our model here, that means we're interested in beta 1, beta 2, beta 3 and beta 4 because we want to know about the determinants of journey time. We want to know how these determinants affect this dependent variable, journey time. And so to give one example, we might be interested in finding out by how much will a 10% increase in line loading affect my journey time. The answer to that is going to be given by this parameter beta 2, or at least beta 2 is going to let us say something about that question. So in L4 we derived mathematical and statistical properties for the simplest form of the linear model with just one independent variable. And we're now going to extend that to the case of the general multiple linear regression model with k covariates. Relative to the case where k equals 1, there are important differences of interpretation and specification that we're going to emphasise. And we're going to introduce, as I said at the beginning, matrix algebra representation of the model to simplify notation. And this representation is going to be used throughout the rest of the course. Okay, so let's have a look at the form of the multiple linear regression model. Conceptually, we're going to assume, or the way I want you to visualize this, is that our observed data are recorded in this kind of form here, essentially a spreadsheet form. So we have n rows that index our observations. We have n observations in total, and each of the columns of our spreadsheet contain a variable. First y, which is the dependent variable, and then the x's, which are the independent variables. And the nice thing about thinking about the data in this kind of very familiar spreadsheet form is that it corresponds nicely to the matrix form of the linear regression model shown below. So the matrix form, y is our n by 1 column vector of observations on the dependent variable. So column vector with n rows. This is just the usual conditional expectation notation, ignore that for the moment. Next we have y equals x. That is the matrix of independent variables in our regression model. It's shown here. So this matrix has, again, n rows, and it has k plus 1 columns. And it has k plus 1 columns because we have k independent variables, but we're going to put in a column of 1s that's going to correspond, as we'll see in a minute, to an intercept in the model. So x is an n times n by k matrix of independent variables, and we're going to assume that this matrix is of full rank. Now, the reason we're going to make that assumption is, in order to calculate the least squares estimate of this quantity here, this vector here, this parameter vector, we're going to have to invert a square matrix. And this square matrix is the product of x transpose times x. I'll show you in a minute why that ends up having to be the case. But in order to invert a square matrix, as you know from matrix algebra, the matrix must be non-singular. And a necessary and sufficient condition for non-singularity of a matrix is that all of the columns of x must be linearly dependent. Now, the rank of a matrix gives us the maximum number of linearly dependent columns. And because we're assuming, and we're going to assume this throughout this lecture, that x is of full rank, it means there's no linear dependence between the columns of this matrix, and that's going to let us go on and invert the square matrix, which is the product of x transpose x, as we proceed. Worth saying at this stage that for those of you who need to brush up on matrix algebra, please do so before the lecture. We don't use anything particularly complex. Even just looking at the prerequisite handout I gave for this course, the mathematical prerequisite, it's got a section on matrices, and that should contain pretty much everything you know. Okay, so that's x, it's this matrix here. Next we have a column vector. So this is a k plus 1 by 1 column vector, so it's got k plus 1 rows of unknown parameters, and that's what we want to estimate. Now notice that x is n by k plus 1 and beta is k plus 1 times 1. So by the rules of matrix multiplication, this matrix and this vector are what's called conformable for multiplication, so we can multiply them through, which is why it's written in that form x beta. And then finally we have the vector of errors. It's an n by 1 column of error terms. So that's the form of the regression model shown here. Y equals x beta plus var epsilon, corresponding to observation I. Now a row of this matrix, a row of this x beta plus e corresponding to observation I is precisely equivalent to the scalar form that we introduced in lecture 4. So yi in lecture 4 we said equals beta naught plus beta 1 xi1 up to beta k xik. So this is the observation on covariate k for, sorry, it's the value of covariate k for observation I. This is the error term for observation I. We can write it as a summation. But using matrix notation, we can write it more compactly in this way. So the transpose of a row of x times the parameter vector beta plus the error term. Just a point here on notation. To avoid confusion, we're going to use bold lowercase x to denote a column or row of the matrix x, uppercase, and non-bold lowercase to denote a scalar value. That's just a convention that's used in the literature. So that's what a row looks like. Note again that x transpose times x transpose is a row vector that is one row by n plus k. Beta is n plus k by 1. So these two are conformable for multiplication and they produce a scalar. Note again, I mentioned it in the slide above, the first column of x is an n by 1 column vector of 1s. So this column vector here, it's just 1. Every row in this column vector takes the value of 1. And this allows for an intercept in the model because the product of x and beta is when the product of the x matrix and beta's form. So that's just going to that 1 is always going to give us a beta naught in this equation here. It's always going to give us a beta naught. And the matrix X is sometimes or commonly referred to as the design matrix. So what you can see is that the form of the multiple linear regression model is essentially the same of that as the simple model, but it allows us to accommodate a matrix of independent variables rather than just a single one. Again, a key distinction we need to make right at the start is between the systematic component of the model, or the regression function, and the random component, or error. So we're going to have to repeat some definitions that we got last week, but we do so in the context of the multiple linear regression model, and we do so using matrix algebra. So the regression function is the conditional expectation of y given x, written in this form here, but because we're using a linear and parameters model, the regression function in the case of the multiple linear regression is going to be x beta. And this systematic component determines how the average value of y changes as elements of x change. That's the systematic component of the model. The error term, or random component, disturbance term, is the difference between the dependent variable and the regression function. And this random component is unobserved. It renders the relationship between the dependent and the independent variables stochastic. So no different than we learned last week, but just in a setting where we have multiple independent variables. So the multiple linear regression model then has a parameter vector beta with k plus 1 elements. And in our journey time example, the regression function that we've just described has this form. It has an intercept, beta naught, and it has 4 slope parameters, beta 1, beta 2, beta 3, and beta 4. So let's think now about parameter interpretation. How do we interpret these parameters beta naught to beta k when we have multiple independent variables? Well, we'll start with the intercept, and really interpretation of the intercept in the multiple model is no different than it is in the simple model, really. It still measures the mean of y when all covariates take the value of 0. That's what the intercept measures, and you can see that that must be the case, because if we just set all of these random variables equal to 0, we would end up with the mean of y at that point. Now, in many cases, the intercept doesn't really make a lot of sense, because it doesn't make sense to set all covariates equal to 0. Let's take the journey time example. What's the expected journey time when distance is 0 and headway is 0? In other words, when there's no distance to travel and there's no frequency of train. Well, that doesn't really make a lot of sense, and in such cases the estimate of the intercept isn't a particularly interesting quantity. However, when it comes to prediction, to compute the predicted y for given values of x, we have to account for the intercept in the calculations. So it's always there unless we have a good reason to assume that the intercept shouldn't be in the model. It doesn't often have a particularly interesting interpretation, but we do need to use it to account for or to make predictions in our calculations. Let's now look at how we interpret the slope parameters. And this is where it's important to understand the difference between the simple and the multiple linear regression model. And that's because in the multiple linear regression model, we're dealing with partial derivatives for each beta. So parameter beta j, an individual parameter from the multiple linear regression model, captures what we call the partial effect. That is, it measures the additive change in the expected response associated with a unit change in x with all other variables held constant. So we can write it, of course, in this form here. Beta j is the partial derivative of the average conditional response with respect to covariate j. Partial derivative. And so they therefore interpret beta j as an approximation to the marginal change in the expected response for a unit change in xj. So this is the approximation we're going to use. We're going to say, think of beta j as telling us what's going to be the change in the expected response for a unit change in xj. Or more generally, if we multiply beta j by a constant, it represents the change in expected response for a c unit change in xj. And notice that interpretation of beta, any beta, depends on the scales of measurements of the covariates and of the dependent variable. And that's because it's measuring an absolute quantity. So let me just give an example. I mean, this idea that we hold other variables constant when we interpret the parameter, so we interpret it as a partial derivative, is sometimes called a ceteris paribus assumption. Ceteris paribus, that is, holding other things equal. And let's have a look at what that means in an example. So the example I'm going to think about, and it's fictitious, but I think it's quite a good one just to demonstrate what we're saying, concerns heart disease, smoking and cycling. So let's say we've got data for a 10% sample of the population of 500 towns, and the data tell us the number of residents who have heart disease, HD, the number of residents who smoke, SM, and number of residents who cycle to work. And we're interested in finding out how smoking and cycling affect heart disease. So we use the data to fit a multiple linear regression model. Heart disease is a dependent variable, smoking is one independent variable, and cycling is the other. And we estimate this model, and the results tell us that our estimate of beta 1 is 0.18. That is, the marginal change in the expected response for a unit change in smoking is 0.18. And our estimate of beta 2 is minus 0.2. That is, the marginal change in heart disease, or expected heart disease given the covariates, for a unit change in cycling is minus 0.2. And the way we interpret these results is as follows. For a constant level of cycling across cities, so if we held cycling constant, then we would expect an increase of one smoker to be associated with a 0.18% increase in the expected number of people with heart disease. So smoking is not a good thing for heart disease, positively associated, and that is the magnitude that we've estimated. For the second parameter, beta 2, for a constant level of smoking across cities, an increase of one cyclist is associated with a 0.2 unit decrease in the expected number of people with heart disease. So cycling is a good thing in that sense. It tends to reduce heart disease, and that is the magnitude that we've estimated. So let's say that over the next year, increased working from home is going to reduce the number of people who cycle to work by 5,000 people. Does this mean that we will expect to actually observe an increase in heart disease? Well, using our estimate for beta 2, we could calculate beta 2 times a fall in 5,000 people cycling equals 1,000. So this calculation predicts that the marginal change based on the partial effect alone, e.g. with the number of smokers held fixed, then a decrease of 5,000 cyclists should be associated with a 1,000 person increase in the expected number of people with heart disease. But let's now assume that simultaneously the number of smokers is going to fall by 10,000. And that's going to happen just because the number of smokers is falling over time as people give up and move to vaping or just quit, whatever it might be. If that was to happen over the same period as this year, as there's going to be a fall of 5,000 cyclists, then the change in smokers would be associated with this marginal change in the expected number of heart disease. It would fall by 1,800. So although a decrease in cycling should in fact raise the expected number with heart disease ceteris paribus, holding other things equal, and it will do, together the combined effect from changes in cycling and smoking would be that we would observe a minus 800% person decrease in the expected number of people with heart disease due to the combination of the two effects. So I hope this demonstrates something important, and that is, if we were just to look at the change in Y outside of our multiple linear regression model and look at the change in each X separately, then this would give us the wrong conclusion. We would end up reaching the wrong conclusion about the effect of both smoking and cycling on heart disease. The linear regression model gives us the partial effect. It breaks it down into these partial derivatives holding one constant, and it tells us actually that cycling is a good thing, even if the aggregate data don't show that because of the effect of smoking over the same period. Okay, just a few more points on parameter interpretation. Interpreting the slope parameters. In some situations, the parameters of the multiple linear regression model can actually be quite difficult to interpret alone. So look at the following two models. In this model, we have two independent variables, x1 and x2, and the model takes the following form: beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x2 squared. Second model, again we have two independent variables, x1 and x2, but the model has the following form: beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2. So if we take our partial effect from model 1, the partial effect on the expected response with respect to x1 is just beta 1, but the partial effect on the conditional response with respect to x2 is beta 2 plus 2 times beta 3 x2. So for x1, the partial response corresponds to a single parameter, but not for x2. And that means that in this model here, interpreting beta 2 and beta 3 in isolation is actually difficult. The reason being that we wouldn't be able to change x2 by 1 unit and simultaneously change x2 squared by 1 unit. In order to get a sense of how x2 is affecting the mean response, we need to use the total partial effect, not the individual coefficients. So we want to interpret the partial effect, not the individual parameters in this case. For model 2, our partial effects are, well, with respect to x1, it's beta 1 plus beta 3 x2, and with respect to x2, it's beta 2 plus beta 3 x1, so that the partial effect of x1 depends on x2 and vice versa. This is called an interaction, and we'll look at it in more detail next week. But again, just to point out that depending on the form of the model, and particularly when it has polynomial terms and interaction terms, interpreting individual coefficients may no longer make sense. We might have to interpret the partial effect as a combination of coefficients, or a combination of coefficients and random variables. Okay, just some final points in this part of the lecture. In general, the effect of a variable x on the mean response, as captured by beta, will differ depending on what x's are present in the model. We'll return to this point throughout the course. It also depends on the form of the model, as we've just seen, and on whether any transformations have been applied, and we'll look at transformations next week. But in terms of the underlying statistical theory, we can develop everything we need to know in relation to this generic model, y equals x beta plus var epsilon. And so these two models here, even though they contain only two independent variables, but three terms, so to speak, x1, x2 and x2 squared, It's all nicely incorporated within this form here, so we don't actually need to worry about what the detail of how this looks in any particular case. This model is general enough to cover all of these examples when we deal with the statistical theory and the mathematical algorithm that we use to derive estimates.